it's me again. Yeah. Thank you for this opportunity for us to give me the second chance to present our work. So I'm going to talk about this Maya civilization collapse. And this is also a collaboration with historian and archaeologist. So let's see that. Okay. This work actually, in the very beginning, it's inspired from a similar workshop that we have had in Sweden, in Uppsala University, with a group of archaeologists. And they are very passionate and talk about this Maya civilization evolution. And so I was just, trying to learn something new because I'm a climate modeler, so not knowing all this, what happened in the past. And then when they mentioned about that, why this collapse happens, because this Maya period actually, it lasted not very long. It's from this 250 to 950, this is this previous period that the society developed very well. They build very large cities, and then they all have all this evidence from archaeologists' sites that showing how society is going well at that time. And they also build this developed very good this trade network, and also agriculture, everything is going very well. So this is actually a small area. You see this Central American, and it's part of this southeast of the Mexico. So then start from 950, actually because of this climate, or also because of the population growth, the society actually has a large pressure for this food or this shortage of the water. Then it's also have some kind of conflict, political conflict. There's wars between the cities. So that's all stories talked by the archaeologists. Then there's also another thing happening that they suggest that during this period that there's a very persistent drought happened. That's even just accelerate this decline of the Maya civilization. So then what we thought, when I heard about that, I said, okay, I just had a new Bacon last millennium simulation. Maybe I can take a look at the climate part. So that's how this work started. So for all these hypotheses of the collapse, of course, that they have these different hypotheses for this society conflict from the political part, and also disruption of this in-trade network, or they also assume that there was some kind of disease also developed in the region, and also about this agriculture practice failure. Of course, this agriculture practice failure related to the climate change. Then eventually it's also climate change also play a big role here. And then first we collected some kind of paleoclimate evidence seeing that how this drought happens. So there are several sites that from the lake sediments or specisms or pollen data, they have showed that how this how the climate changes in the past, so during that period. So this is presented in a review paper by Douglas in 26. I think this is a great kind of symposium that for all these different evidence. So this evidence from different proxy data, I will not go through each proxy data, but they all showing something that happening during this period. So that's also all consistently pointed to some kind of climate change. And then they also summarize that not only in the northern part, but also in southern part, both showing this drought. Or if you just combine all the proxy data together, they all indicated this. So that means that we already have evidence from the paleoclimate data. So next step, we try to see if we also have this, we can see this in our model. So because at that time, I just finished a last millennium simulation, so we were able to look at that. So from the paleoproxy evidence, when you read papers, you see that all the papers, usually they ended with some hypothesis that they want to explain what we see is related to what caused all this for these mechanisms from the paleo prox data, actually they have different suggestions. So first, all the data, they show this kind of Maya lowland droughts, that's no doubt, but the explanation is actually different from the different proxy data. So some data authors, they say that, okay, it's due to the solar radiation, because we know there's a high solar radiation at that time. And then some suggest there's a weakening of the AMOC, this Atlantic Meridional Over Circulation. This is weakening. And some suggest it's a southward shift of the ITCZ. And some suggest there's increase in enso variability. And also pollen data says also there's some deforestation. So if we look at all these mechanisms, actually, if we have a simulation, we actually can take a look and investigate and see if what all these hypotheses are correct or not. So that's what we do in the next step. So we use our last millennium simulation. So this is also part of this PMAP simulation that we do the simulation from 850 to 1850. This is a transient simulation. Transient simulation means that this simulation is different what the simulation that I talked on the first day about the sensitivity experiment. For the transient simulation, we use the actual forcing, like we have orbit forcing, greenhouse gas forcing, total solar radiance, and also volcanic aerosols, and also land coverage. We even already can take into account of the anthropogenic land use in this simulation. That means that when we do this simulation for the last 1,000, this actually kind of mimic what happening in the last millennium. So it's so you can also compare this with prox data and also try to understand what's happened in the last millennium. Of course, there are also some other changes like aerosols and ozone ice sheet. They very small. So we did. First, we don't have this kind of detailed data, and then we didn't consider that into simulation. So we keep them as the same as the pre-industrial. And this is the forcing that you see that for the volcanic forcing, greenhouse gas, and insolation, and solar radiance. So that's all the forcing that you see that it also changes along the time. So that's the evolution. We also know that for the last millennium, actually it's very stable climate. There's not much thing happening like what you see that in the past DO cycle or very glacier interglacier change. That's not very dramatic. So it's very stable. But there's some, for the last millennium, most important forcing is the volcanic forcing. So this also kind of, we thought about that one reason of the cause the late ice age, because in the last millennium, there's two kind of period. One is the medieval warm period and one is the late ice age. Then it's very stable climate, not much happening there. So then with this simulation, we take a look at, because we are thinking about if we can reproduce this drought, of course, then we first look at these climate variables like temperature and precipitation. So if we look at the temperature and precipitation, even for this small region, we could see that the temperature shows the medieval warm period and the late ice age. So, and then for the precipitation, there's more variability, but we do see there's less precipitation during this period. That's what they suggest is the drought period. And then we know that for the drought, you not only think about the precipitation or only its temperature, but the combination of these two. So there's also another climatic drought index called SPEI, Standard Precipitation Evapotranspiration Index. So we also calculate this. This also takes into account both temperature and precipitation. Then you could see actually SPEI shows strong, very severe drought during this 300 years long period. And then we also take a look at other model, because that's only from our model. We want to see if the other model is, if other PMAP model is also showing this. So we also take a look at other four models. So except this temperature and precipitation, if we look at SPEI, we could see that actually this French model, this IBS error model, it shows also very similar to what Easy Earth shows. And also another, this Japanese model, MRR model, is also shows some period of this drought. And in some other models, the drought is also showing up, but not very strong as showing in the EC Earth model or in the IBS error model. And then next, we want to use this model simulation, try to see that, or try to verify all these suggested cause of this drought from the proxy data. If we also can see that in our model. So this includes several ones that they have suggested, like I showed this proxy data evidence. There is only this one, that's tropic cyclone frequency is only suggested by one proxy data, so it's very uncertain. But we also can test that in our model. First, we look at this precipitation. Here, I also marked out where this is Maya lowland in the global picture. If you can take a look, then it says it's a very tiny, small region in the Central American. And this is climate mean or climatology for the last millennium. And you could see this is where this precipitation goes. It's ITCZ actually, usually follows ITCZ. And then this is anomaly during this dry period. Then if we look at this blue one, it means that less precipitation. That means that you could see actually it's a large area, less precipitation, dry. It's not only this region. This region actually is also in the margin of these larger ones. Actually, precipitation decrease in the tropic Atlantic. So that means this is only part of this regional climate change. And from here, we also can see that because this region is so dry, and that they also indicate this southward shift of the ITCZ. So it's kind of verify one of their hypotheses from the proxy data. And then about this solar radiation. So this solar radiation is different from the orbital force. The orbital is only just shows this distance between the sun and the Earth. It's the solar radiation, how it distributes over the ocean. But solar radiation is how strong the solar itself that giving out the solar radiation. So what we see that there is slightly high radiation. Actually, it's a forcing for our model. So it's not like what models simulated, but it's from the reconstruction, and we use this as a forcing to force our model. So this is also consistent with the temperature, what temperature responds to this high solar radiation. But it's actually, it's not very strong. It's a very weak forcing. And then we also just want to look at this ENSO variability and also AMOC variability. First, if we only look at this sea level pressure, this standard deviation for the global, we could see from the standard deviation, we see that SST in the Eastern Pacific have an increased variability, and we see this AMOC have a decreased variability. And then further, if we look at this index for this ENSO, usually we use NINO34 index to represent ENSO activity, and also for this sea surface temperature over the North Atlantic to represent AMOC activity. Then what we see that during this period that we see that actually you have this very strong or warm SST in the Eastern Pacific, and this is also corresponding very well to the AMOC decrease. So this is what we think that maybe this AMOC decrease happened first, because this is kind of ocean activity from the deep ocean. Then it might also affect the Eastern Pacific. Then further it will affect the ITCZ change and affect this precipitation in the region. There's also some suggestions about this interoceanic SST gradient between this Eastern Pacific and the tropic Atlantic. Then we see that For this drought period, we see this warmer Pacific. We see this is strong. That's also due to this very persistent El Nino event, what we see in the previous slide. But we see that even for the tropic Atlantic, if it's also slightly warmer but less warmer, that means this gradient actually is still exist during this East Pacific and tropic Atlantic. This will suppress the precipitation in this region, in the Central American. And then for this one data suggested this decreased tropic cyclone. We also calculate this hurricane genesis index to see that during the dry period, if there's decreased tropic cyclone, then this also shows in the Eastern Pacific the tropic cyclone genesis is also decreased. So by so that after just invest all these different aspects, oh yes, there's one more aspect is deforestation. This is not supported by the reconstruction because in our simulation we use the reconstruction as a forcing, so we can't really see this deforestation in this simulation. But in the future, when we have the dynamic vegetation, but not use the reconstruction, we might see that. So only this one didn't verify from our simulation. So then to summarize that, then we could just summarize one by one for each reasons that or causes that suggested by the paleoclimatologist from our model simulations. We see for the solar activity, we see yes, because then it's a climate forcing into our, that with the higher solar radiation, we have a higher temperature, much warmer, and that's also why we have this warm, mid-warm period. And for the North Atlantic climate variability, we do see that it's reduced. And we also can see from the shift from the precipitation pattern, we also could see the southward shift of the ITCZ. Then from the Nino index, Nino 3-4 index, we also see this enhanced with more El Nino event because we see all these warm events in the Eastern Pacific. So for the deforestation, as I mentioned, it's a reconstruction. It's not supported. And for the tropic cyclone frequency, we also see that reduced in the Eastern Pacific. And we also see the enhanced Eastern Pacific tropic Atlantic gradient that also shows in our model. So this is all explained. Of course, in the end, we also need to trace how these different how they are interconnected, so which one start first? Of course, as I suggest, it's maybe AMOC start first, then affect the ENSO, then affect the ITCZ, then affect the precipitation. So now we come to this summary. So first, we are very happy that we could see this 300 years persistent drought in our simulation. It's reproduced. That also shows that the model has the capability to capture some of the events that happened in the history. And then we also tested all these different reasons why I call this 300 years drought. So we have these different explanations, and also some also confirm what paleoclimatologists they suggested. So in the end, we also see that the potential of our climate modeling into this climate change and climate variability study even for the past. Like this Maya lowland is a tiny region, and because when we use the global model, we also could see that how this far away, like from the ENSO or from AMOC, can affect this small place, because this is due to the remote forcing. So this is advantage that of the global model, that you not only see the local response, but you also could see the remote or interconnection, or what we call teleconnection in this model system. So yeah, that's all. It's all time.